In this lesson, we want to look at something called the rational root theorem. And the rational root theorem says this. It says, all possible rational roots that I have in a polynomial are in the form P over Q, where P stands for the factors of the constant and Q stands for the factors of the leading coefficient. All right, there's your rational root theorem. What does that actually mean? Well, first of all, let's notice a couple of really important words in this statement. First, the word possible. The possible means they may not all be factors or roots of a particular function. The second one is rational. If there is a root that's an irrational number, the square root of 3, the square root of 7, then those will not show up in this list. We're just looking for rational roots. So they don't all necessarily work out, and we're only looking at rational roots. So let's look at how this actually works. First of all, I'm talking about P being the factors of the constant term. The factors of the constant term. The constant term here is 5. And Q is the factors of the leading coefficient. The leading coefficient here is 2. And we're going to use some very simple numbers on this very first one so that our list is pretty short. Well, that means that P is given as all of the factors that could make the number 5. Well, how can I make the number 5 by multiplying? Well, I could do 1 times 5, or I could do -1 times -5. You'll learn very quickly to always take into account both the positive and the negative of your function. Alright, so if the only ways to make 5 are 1 times 5 and -1 times -5, then we can state that the factors here are positive and -1 and positive and -5. Let's do the same thing with our 2. Q would be the factors of this leading coefficient. The only way to make 2, 1 times 2, or -1 times -2. So I can list my factors of Q as being positive and -1 and positive and -2. So it's told us in the rational root theorem that the possible rational roots were in the form P over Q. So if I list all of those factors over each other, positive and -1, positive and -5, over positive and -1, and positive and -2. What combinations of factors can I come up with that gives me this list that I'm looking for? Well, I could do 1 over 1, and 1 over 1 is equal to 1. You'll learn to do this as you go along instead of writing this down twice, but 1 over 1. I could do 5 over 1. And again, positive and negative, so positive -5 over positive and -1. 5 over 1 is 5. So the second number in my list is positive and -5. Or the next one is 1 over 2. Positive and -1 over positive and -2. Well, that's 1/2. So plus and minus 1/2. And then plus or minus 5 over plus or minus 2, which gives me plus or minus 5 over 2. That's my list of possible rational roots. Well, are they all rational roots of this polynomial? Well, obviously not. This is 2x cubed. It's a third-degree polynomial. How many possible roots does it have all together, whether they're rational, irrational, real, or complex. Well, it can't have more than 3, and I've got a list that's got 2, 4, 6, 8 possibilities here. It doesn't tell me that these are all roots. It tells me that this is the list of all the possible rational roots. Now, there are a couple ways to determine if any of them actually are. I can make a t-chart. I can plug all of those values in. I can run a table on my calculator. I can verify whether or not they are actual roots by substituting each one of these in turn into this function. All of those are valid methods for determining which ones actually work out to be roots. In this case, the only actual rational root is -1. If I do f of -1 in my function, I get 0. It's the only one that actually works out is f of -1. It is the only rational root. But if I need the list of possibles, this is my list of possible rational roots. All right, so let's look at one more example of this, and let's use a polynomial that's going to have a longer list so that you can see what happens and how we verify which one of these we're going to use. Let's use the polynomial function 15x cubed minus 32x squared plus 3x plus 2 equals 0. So there's my polynomial function, and I'm going to look for my list of possible rational roots. My list of possibles would be given by the factors of the constant. So in this case, the factors of 2 over the factors of the leading coefficient. Well, what's the leading coefficient in this function? It's 15. So factors of 15. That gives me, what are the factors of 2? Plus or minus 1 and plus or minus 2. Only factors that I've got for this particular one. Plus or minus 1 and plus or minus 2. But there's a little bit longer list for 15. I can make 15 with 1 times 15, or I can make it with 3 times 5. So my list here is plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. So I now have to come up with every possible combination of a factor in the numerator and a factor in the denominator. So I could have 1 over 1. Well, I'm going to go ahead and reduce. That's just equal to 1. Positive or negative, but 1. I could have 2 over 1. So plus or minus 2. I could do 1 over 3. So plus or minus 1/3. It's rational. When it's a fraction, it's not an integer, but it's still rational. I could do 2 over 3. Plus or minus 2/3. I could do 1 over 5. I'm just coming through my list, putting every possible combination of numerator and denominator. So plus or minus 1 over 5, plus or minus 2 over 5, plus or minus 1 over 15, and finally plus or minus 2 over 15. So in this particular problem, I just moved my thing here, so we'll have to try and stay out of its way here. I have this huge long list. Well, which ones of them work and which ones of them don't work? Well, I could do lots of things. I could test every single one of them. That would be a long list. 1, 2, 3, 4, 5, 6, 7, 8 possibilities, and then they're all positive and negative, so there's 16 different ones of these that I could check. When I was in high school, I had to check them until I found one that worked. I don't want to have to do that. Take your calculator, graph it, and look and see which one of these looks like it might actually be a rational 0 of this function. And if I do that and I look, it tells me that x equals 2 appears to be a 0 of this function. So I have a factor here of x minus 2. So if I do that, let's test this 2 and see if it works. Well, how can I do that? Well, let's use synthetic division. put the 2 in the box, and set up synthetic division. 15, negative 32, 3, and 2. There's all my coefficients. First number comes down. Multiply by the number in the box. Gives me 30. Add down. That gives me negative 2. Multiply by the number in the box. Negative 4. Add down. Negative 1. Multiply by the number in the box. Negative 2. Add down. And I get 0. So this remainder is 0. So we know that that is indeed a factor. X minus 2 is a factor of this polynomial. X equals 2 is a 0. That leaves me with a polynomial 15x squared minus 2x minus 1. And that can be factored in. At this point, you should know the methods to get that in factored form. It factors as 5x plus 1 times 3x minus 1. If I set each one of those factors equal to 0, 5x plus 1 equals 0 gives me x equals negative 1 over 5. And 3x minus 1 equals 0 gives me x equals 1/3. So now I have all of the zeros of my polynomial. I know that the zeros of my polynomial are x equals 2, x equals negative 1/5, and x equals 1/3. So I can write this in factored form if I want. Right? If I want to write it in factored form, I just write each one of the individual factors here, and my factors are x minus 2 times 5x plus 1 times 3x minus 1. And anytime I can get this down to a set of linear factors, I like that. My zeros of the function are 2, negative 1/5, and 1/3. So out of that list of 16 possibilities, there were only 3 that were actual zeros. So be careful when you read the question. Is it asking for the actual zeros? Is it asking for factored form? Or is it asking for the list of possible rational zeros? If it is, it's looking for this entire list of possible rational zeros.